Good morning, everyone. Let's get started. Welcome to lecture 4. Today, we're going to talk about, again, algorithms for arithmetic. We have seen how to use divide and conquer. This point I've said it many, many times. Karatsuba was for faster integer multiplication.
I think, Professor, you're muted. I cannot hear your voice.
Oof.
I am.
I think it's
I can
working.
hear
you.
I think
I can hear.
Okay. All right. So, good, great. I'm glad that things are good on my side. I hope you can figure out settings on your side. Karatsuba is for faster integer multiplication, which let us go below n squared to n to the log base 2 of 3. So Strassen for faster matrix multiplication, which enable us to go below n cubed, which is kind of a naive algorithm, to n to the log base 2 of 7. And today we're going to instead study faster polynomial multiplication. Okay, so multiplication of polynomials, which will let us go from the naive n squared algorithm to n log n, which is extremely good. The key tool that underlies this pretty huge speed up is the fast Fourier transform. Okay, abbreviated FFT. Okay, so FFT itself is not about polynomial multiplication. It's about a related problem that we'll see soon, but it is the main, let's call it enabler, that underlies fast polynomial multiplication. Also, unlike other asymptotically fast algorithms, for example, we mentioned in the first lecture that today we actually know how to do fast integer multiplication in n log n. That algorithm is primarily of theoretical interest, whereas quite beautifully, the fast Fourier transform is an extremely practical algorithm in that it's not just a theoretical curiosity, but this n log n that you achieve for polynomial multiplication is something you can fully take advantage in practice, and people do. And indeed, because of that, the FFT has numerous applications across pretty much all sciences and engineering, recurring sort of applications involve signal processing, for example, switching between the frequency domain and the regular domain, and also coding theory. So for example, for encoding messages in a way that is redundant, and you can sort of check and detect and correct mistakes in communication. And the FFT is also a divide and conquer algorithm, okay, for a particular problem that is not polynomial multiplication, but it is polynomial evaluation. So that is the problem that it solves, okay? There's a question about, why is the n log n of theoretical interest? In the first lecture, we talked about recent asymptotic improvements to integer multiplication that to date is known in n log n, but the constants involved hidden in the big O notation are pretty substantial, so that it's not something you would use like on many inputs of practical interest. That is not the case for the FFT, where the n log n that you get has like a leading constant. It's something like 4. Okay, so it's like a very small thing. It's a pretty very useful algorithm. Okay, so that's the plan for today. We're gonna learn how FFT can help us multiply fast and what it is. So let's review the problem of polynomial multiplication. We are given 2 polynomials. Okay, now we have to agree on how the polynomials are specified for us. So let's say that both polynomials have degree d. Okay, so here they are, a of x and b of x. And the input to us, they're presented to us by the list of coefficients. Okay, so it says, here's the coefficient for the constant term, here's the coefficient for the linear term, the coefficient for the quadratic term, and so on and so forth, for the first polynomial and the second polynomial. Okay. And the problem of polynomial multiplication asks us to compute the coefficients of the product polynomial, okay? And how many coefficients are there? I already kind of messed it up here. There are 2d plus 1 coefficients, because when you multiply 2 polynomials each of degree d, the product polynomial is going to have degree 2d. All right? So that is why over here in the output, we're going to output 2d plus 1 coefficients, okay? Starting from, of course, the constant term all the way up to the term for the power 2d, okay? Just so that we kind of warm up to remember what is polynomial multiplication, there's a naive algorithm that just basically takes the definition of polynomial multiplication and turns it into an algorithm. Let's remember that the definition of polynomial multiplication is as follows. C of x is defined to be basically the product of these two formal expressions, which once you open them up, it is the sum from I equals 0 to d, then sum from j equals 0 to d of ai bj xi times xj. Okay, so that's, I just opened up the expressions formally. But then, it's not very helpful. It doesn't really tell us what is the coefficient of any particular power, because there are different combinations of xi times xj that give us the same power. So I want to gather all coefficients for the same power together. So let's do that. So now I'm going to sort of relabel things, and I'm going to sum from 0 to 2d. And I'm going to consider all possible combinations of coefficient multiplications that correspond specifically to the power x to the I, right? Because here, look, we're multiplying all the pairwise, we are considering all the pairwise products, and whenever I and j sum to a particular power, here called I need to consider all the possible combinations of I and j that sum up to it. So here I'm calling them, k and I minus k. These are all the possible combinations that produce the power x to the I, okay? So this is telling me that this is the coefficient ci of the power x to the I, okay? So the naive way to compute the product polynomial would be to say, okay, well, if this is the definition of each of the coefficients, let's just take each coefficient and compute it one at a time. So the naive algorithm would say for I equal 0, 1, all the way up to 2d, we're going to compute ci, it's a pretty ugly C, ci, which is that expression contained in a parenthesis up there. Right? So that's what I mean by we just take the definition and we turn it into an algorithm. We just take the definition and turn it into an algorithm, right? Can anybody tell me, what is the running time of this algorithm? There's a loop involving 2d plus 1 things, right? We're repeating the loop 2d plus 1 times. And within each iteration, we have order of d work. And in here, correctly in the chat, many people are suggesting quadratic time. So here we have a running time that is order of d squared. Okay, not surprising. We're kind of considering all the possible combinations of objects of size d that's we're going to pay for the quadratic term. Okay, this is not an awful algorithm, but quadratic things grow pretty fast. Also, just because the output has size d and kind of each coefficient of the inputs affects the output, we really cannot expect better than linear in d. So like every algorithm for polynomial multiplication must run in at least d time. So really we're just haggling between d squared and d. Can we do as close to d as possible? Okay, so that's the question we ask. Can we do better than order of d squared operations? Let me just pause here for a moment. Are there questions about the problem statement and the naive algorithm? Okay. All right, let me just explain again, why is it order of d squared? So here we have 2d plus 1 iterations, okay? And then here, we have a sum that involves order of I terms. But when I is order of d, then those two things multiply. So you're going to have basically a, order of 1 plus order of 2 plus order of 3, all the way up to, order of d. That is order of d squared. So that is the cost of this algorithm. All right. Okay, now the starting point of realizing that maybe we could do better than the naive algorithm is that actually multiplication of polynomials is not hard if you want to multiply polynomial evaluations. So for example, let's say you give me an input to u, and rather than asking you to compute c of x, the coefficients of c of x, I ask you, how about the value of the polynomial c at the input u? Well, look, by definition, that is the value of the polynomial a at u times the value of polynomial b at u. And how many multiplications do I need if I am given au and bu to obtain cu? 1, right? So like at a particular point, if I'm given the evaluation of a and the evaluation of b, deriving the evaluation of the product polynomial is just 1. It feels like I'm saying something a bit silly, but it's not too silly in the sense that, look, c is like potentially a complicated combination of a and b, right? But because of this expression here, at kind of this point-wise evaluation, actually polynomial multiplication is very simple, okay? It's just 1 multiplication. More generally, if I'm given many evaluations of a and many evaluations of b, I can, in linear time, derive many evaluations of c, simply by doing point-wise multiplication. So this suggests an approach. What if we start from the coefficients of a and b, we evaluate them on many points, so we get many evaluations of a and b, then we point-wise multiply, which is easy, okay? And then once we have enough points to determine what c is, we interpolate c back. Okay, and now we're going to work out this plan a lot more precisely, but the point being here is that the starting point of, why does polynomial evaluation and interpolation have anything to do with polynomial multiplication, is that polynomial multiplication of evaluations is much easier. You can do it in linear time. So we're going to kind of move in the so-called evaluation domain, multiply things there, and then move back. Now, of course, this is worth it if evaluating polynomials at many points and interpolating polynomials is faster than d squared, okay? Otherwise, why are we doing that? We could have already paid for d squared the naive way, okay? So it's unclear at this point that we made progress, but we have at least laid out a credible plan for trying to attack the problem. We're going to try to solve evaluation problems faster than d squared, interpolation problems faster than d squared, specifically in d log d, each of them. And then this stuff is order of d. Again, we're going to do it over this more precisely in the next few slides, but this is kind of the plan ahead of us. Now, because we're talking about coefficients and evaluations and everything, we need to take a short interlude into this dual representation of polynomials. Okay, so let's start with a maybe very simple case, a line. So what is a line? That's just a polynomial where the degree equals 1. So for example, you can have a of x, which in this case is a0 plus a1 of x. Okay, and you may sort of, in this special case, these coefficients even have names. This is called the intercept, because that's where kind of a of x touches the y-axis at x equals 0, and this is the slope. Okay, they're so familiar to us that we even give them sort of specific names rather than a0 and a1, right? Now, that's one way to represent a line. But another way to represent a line is to just give me the values of the line at any two distinct points. It says it goes through here and it goes through here. And it's kind of visually clear that there is a single line that goes through these points and no other line. So that's just another way to tell me what the polynomial is. Rather than giving me the coefficients, you give me the valuations at 2 points, okay? Now, these representations are equivalent in the sense that I can move from this representation to this one. How? Well, if you wonder what is the value of the line at u0, well, you set v0 to be a of u0. Duh, right? I mean, that's the value of the line at u0. And this is the value of the line at u1, okay? So that's how you move from left to right, okay? And the way you move from right to left is something you may be familiar with. You're basically interpolating, but one way to do it is you write a of x equals v1 minus v0 divided by u1 minus u0. This is kind of the slope. Then you have like a small shift. And then you have like a constant offset. And it's easy to verify that this polynomial really passes through these 2 points, right? Because when I evaluate a at u0, well, this entire term goes away and we get v0, which is what we wanted. And if I evaluate a at u1, then I'm going to have u1 minus u0. So these things cancel. I'm left with v1 minus v0 plus v0. So everything simplifies to v1. So this indeed is the expression of a line that goes through these 2 points. Okay? So we have seen how in this very simple example, we can move between these 2 representations. And of course, it is crucial that the 2 points you give me are distinct. Otherwise, I can't specify the line, right? If you just give me twice the same evaluation, then there are many lines that go through it. So that's not okay. And this algebraically comes up, for example, in this denominator, that would be not defined unless u1 and u0 are distinct. Okay, these lines are just the simplest cases and the one that maybe we go over a little bit more carefully. You have also probably seen lots of quadratic polynomials. These are kind of parabolas. In this case, they're specified by any 3 points, okay? And you move this way by evaluating, and there's also some interpolation you can do on the way back. We'll kind of come back to that later. The point here is that I want to point out the pattern that for a degree d polynomial, you have to give me d plus 1 distinct points, okay? So it doesn't matter where they are, you just give me the value of the polynomial at any d plus 1 points. And I can go here and I can move back, okay? One is evaluation, the other one is interpolation, okay? And so these are the 2 basically sort of general operations, coefficients to evaluations. So you give me the polynomial and I evaluate it on a set of points. And the set has to be large enough, maybe even larger, to uniquely identify the polynomial. And I'll just point out here that there are many choices. There are many choices of such S. Okay, so our choice of which kind of domain over which to evaluate the polynomial just needs to be large enough, but otherwise this kind of equivalence doesn't care. And today we'll make explicit use of this degree of freedom because we'll pick the set S to be very good for us, to have like a lot of structure, okay? Now the reverse direction from the evaluations to the coefficients, right? Such that they agree with evaluations. This is something that is known as interpolation. There are various ways of interpolating. One of them is that is, in my opinion, particularly intuitive to think about, is called Lagrange interpolation. We're not going to go through it. You may in discussions, I'm not sure. We're anyways not going to need it. But in general, at this point, let me just, if you don't want to know necessarily what is Lagrange interpolation, I'll just say that this is just a linear system of S equations in the variables A0, A1, up to AD, right? Because you want to find the AI such that these things holds, okay? But this is a linear expression in the I, and this is some constant. So you have just a linear system in S equations. So it's not surprising that in order for you to uniquely determine the variables, you need S to be of size at least d+1. Okay. So that is maybe, like a high-level explanation for why, this S+1 is there. Okay. Anyways, and there's a way to explicitly, there's an explicit solution to this linear system, which Lagrange interpolation is such. All right. Any questions about the dual representation here? Okay. So remember, the inputs to our problem are in coefficients. We're going to be using the evaluation representation to kind of do multiplication in a different domain, essentially, and then we're going to switch back. Okay. And multiplication in this domain is easy. We're going to have to figure out how to make these things fast. Right? Any questions about the representation of polynomials? So there's a question about whether S is too big. No, S is not, can never be too big. I mean, we're going to, obviously we want S to be at least d+1 and not much larger than d+1. But if it's too big, it's just going to make our algorithm slow. But it's not gonna cause any problems in the correspondence. For any S for which this is the case, you can go back and forth. And we will choose S. So we can shoot ourselves in the foot and choose S that is enormous, and then our algorithm efficiency will go out the window. But we will deliberately pick S to be at least d+1 and not much more than d+1. Okay. We have a lot of leeway on what S is. And evaluating a polynomial at one point is an order of the operation. The difficulty is that we want to evaluate the polynomial at many points, and so that may be a quadratic operation. That's what we're going to see in the next slide. That's what makes this non-trivial. Great. So now that we have formally discussed the two representations of polynomials, I would like to make precise how we derive a multiplication algorithm from evaluation and interpolation operations. Okay, so that then we can just worry about the problem of polynomial evaluation. So let's try to write a multiplication algorithm for the polynomials given by the coefficients a0, a1, a2, and so on, so up to a d, and then the other one given by b0, b1, up to bd. Okay, so those are our polynomials a of x and b of x represented as coefficients, which we want to multiply. So the template algorithm will say, okay, let's pick some domain S, and we want S to be of size at least what? If I want to represent uniquely determine D, sorry, not D, uniquely determine C, the product polynomial, how big should S be? Right, 2d+1, not d+1, right? Because remember, I want to uniquely determine the product, and the product has degree 2d. So here it's going to be of size 2d+1. Then what we're going to have some evaluate subroutine that will take our polynomial as coefficients, and it will evaluate it on the set S. And what will come out is, well, the evaluations of A on S. Then we're going to do the same with B. Okay, and what's going to come out is the evaluations on over S of B. Now that we have the evaluations of A and B, we can pointwise multiply to get the evaluations of C. Right? Once we have the pointwise evaluations of C, we can now interpolate. So we're going to tell the interpolation algorithm, please interpolate to obtain the polynomial that corresponds to the kind of pairs of location value given by U, CU, where U ranges in S. Okay? And this subroutine is going to return to us the coefficients that correspond to that polynomial. Okay? And because we have chosen S to be large enough to uniquely determine C, then this algorithm returns the correct answer. Now, the running time of this algorithm is going to be 2 times the time to evaluate a polynomial of degree D plus order of D. This is step number 4, right? For the pointwise multiplication, plus 1 times the time to interpolate something of degree 2D. Okay, so essentially what we have established here is that we have a plan for polynomial multiplication whose cost really depends on the cost of evaluation interpolation of polynomials. All right. And the fast Fourier transform will enable us to do eval and interpolate in D log D operations. So this leads to polynomial multiplication that is in order of D log D operations. Why? Because we will have 2 times order of D log D plus order of D plus 1 times order of D log D, and everything ends up coming out as order of D log D, okay, which improves on the D squared. We haven't seen yet how to do it. I'm just telling you that we'll see how to do it, and because we will be able to do it, then we'll be able to get polynomial multiplication in order of D log D, okay? And for the rest of today, we'll kind of ignore interpolation. We'll just talk about evaluation. And I presume that in homeworks or discussions, you will talk about the mirror operation of interpolation, okay? All right, so we're going to talk about polynomial evaluation. Before we do that, are there any questions about this? All I've done here is I've turned slightly more precise our previous plan. There's a question about whether these steps 2 and 3 are recursive calls. They're not, right? Because we are underneath the algorithm multiply, and we're invoking a different subroutine that is about a different problem. It's saying, please evaluate, okay? Now we'll construct evaluate in a way that is recursive with respect to evaluate, but this is not relative to multiply. It's not a recursive call, okay? And why are these D log D? Because I've said that they are. I've said that thanks to the FFT, we'll be able to make all the green things D log D. Okay, so that's why I've replaced them by D log D. We haven't seen yet how to do that. Okay.
There are another couple questions about the domain and how big S is again.
Okay.
Yeah.
All right. So why does S needs to be of this large? Because remember, we talked that to specify a polynomial, you need to give me degree of the polynomial plus 1. The polynomial that I would like to uniquely determine is C, and C has degree D plus D. So it has degree 2D. Therefore, I need to have a domain that is large enough to uniquely determine C. So that would be 2D plus 1. And how are we going to choose the domain? Well, we're going to choose it later to be whatever we want. I mean, as long as it satisfies this condition, we're going to be fine. All I'm saying is that for multiply to be correct, it doesn't matter where S is, as long as S is large enough. But for the correctness of multiply, all we care about is the size of S. Okay. Now, of course, the bigger S is, that it's going to change the evaluation. So you should think of S as being, order of S, so order of D, in terms of size. All right. So
there's just a few questions about how this interpolation is going to work, and how we're going to do interpolation, I guess.
So we're not going to talk about interpolation today, but we said that what it is. Interpolation is defined to be the operation that takes the evaluations of a polynomial and interpolates. Like that's the definition. And right here, it doesn't matter how we're going to achieve it, as long as this subroutine does what it's supposed to, interpolates, then this is going to be a correct subroutine. I mean, a correct multiplication algorithm for polynomials. We'll not talk about interpolation. It is kind of a dual of evaluation. So for now, just going to ignore it. How we achieve it, we haven't even talked about how to achieve evaluate, by the way. But whatever way we achieve it, as long as we achieve it, this is going to be the coefficients of the product polynomial. Are there any other questions that I missed, or?
I think we're good for now.
All right. Okay, so henceforth, we are going to talk about just polynomial evaluation. Okay. And look, the naive algorithm is pretty straightforward, right? You just, if you want to evaluate your polynomial at everywhere on S, then you just pick each element of S and you evaluate the polynomial at that point. So you can say for U in S, you're going to compute AU, which is just the expression. You sum I equals 0 to D of AI U to the I, right? That's, I mean, if I have to evaluate A everywhere on S, the straightforward way to do it is like this. I know how to evaluate the polynomial at one point, and I'll just keep doing that for every point in S. So this is going to cost me size of S times D, right? Because this expression costs me order of the operations. By the way, you may wonder, why isn't it D log D? Well, there's a way to evaluate as a whole thing using order of the operations. We might do it later in the course, but it's a cute, simple way. So this can be done in order of D. So size of S times D. And remember, S has to be of size at least 2D plus 1. And let's say that we are able to pick it to be, order of D at most. So this is going to be, in the end, order of D squared. Okay? So this is telling us that, if we don't think too hard about polynomial evaluation, we're back to the quadratic regime, which is not surprising. I mean, at some point, we have to introduce some idea. Okay? But so is it clear why naive polynomial evaluation at many points is a quadratic operation? Great. All right, so the fast Fourier transform is going to be an algorithm that will help us evaluate polynomials faster, okay? And before we look at the algorithm, we're gonna build up the intuition for it, okay? So, going back to the previous question, should we use 2D plus 1 points?
What's D defined to be exactly?
D is the degree of the polynomials. Right?
I think that the question is stemming from why the algorithm recurrence relation is written with D as the input for some places and 2D for others. I think it was just, maybe we could clarify that a bit.
Okay, well, so let's look at the evaluation here. I'm invoking the evaluation algorithm on an input size D, right? So I'm defining the input size to be the degree of the polynomial that I want to evaluate. I could also say D plus 1, but this is just a matter of definition, right? And really, if I want to be super precise, evaluation actually has two parameter inputs. There is D and S, okay? So you shouldn't pay, too much attention on what's here, whether it's D, D plus 1, or D comma S. The point is that, we're going to pick D and S to be order of D. And so I'm invoking eval on something on input of size D. But really, like, evaluation is like an operation in general that has two parameters: the degree of the polynomial and how many points you want to evaluate. But here we're going to pick S eventually to be of size order of D. And here I was just emphasizing that we're going to be interpolating, 2D plus 1 points, and you can define the problem to be about that the input size is either S or S minus 1 to be the degree of the polynomial that you interpolated off. So these are not very important. What matters is that D appears inside it, with the plus 1 or the 2 in front. It's not very important. The main point, all I wanted to say is that, this is the cost of this thing here, and this is the cost of this thing here, and we'll make both of them D log D. Okay, any further questions about this slide? So all we've done is basically reduced polynomial multiplication to evaluation interpolation, and we'll specifically talk about evaluation. Again, keep getting this question, why is interpolation time d log d? Because I say so. We have yet to show it, and the FFT will show that. And we'll actually only show it for evaluation, but interpolation is kind of a dual operation, and I think it will be discussed in discussion sections. And I stress, we haven't really said anything yet. Like, we haven't even seen the FFT yet. We've just basically sort of distilled the problem to the core, which is solving this evaluation problem. Now we're going to do it now, okay? Because we haven't yet introduced really any, I mean, we've done a little bit of progress in terms of simplifying the problem to some basic, more simpler problem, but we haven't really introduced any real ideas. In particular, we haven't even used divide and conquer yet. Okay. So at a very high level, the main idea to make progress to achieve a faster polynomial evaluation algorithm is that we're going to make a very clever choice of S so that we're going to support a divide and conquer approach, okay? So we're going to try to say, okay, if you want to evaluate a polynomial on S of size, D, then, here's some approach, and all you really have to do is to evaluate polynomials on size half of S, okay? And so on and so forth, okay? So we're going to try to relate polynomial evaluation to polynomial evaluation in smaller and smaller domains so we can do a recursive divide and conquer approach. Now, so now we have to start with some guesses about what the divide is, okay? Never mind the conquer. So polynomials, there is a natural way to split a polynomial into two polynomials of half a degree, which is you gather all the even coefficients and all the odd coefficients into two smaller polynomials. So for example, let's do it for this polynomial here. So I have this polynomial a of x, which is 4 plus 12x plus 20x squared and blah, blah. And I can write it as a polynomial which collects all the even coefficients. And yes, when I said even and odd coefficients, I specifically mean the coefficients of odd and even powers. Obviously, I'm not looking at whether the coefficients are themselves odd or even. So first, for the coefficients of the even powers, I would gather 4, right? Because it's 4 times x to the 0, and 0 is even. I would write 20x squared because 2 in the exponent is even. And then I would write 6 times x to the 4th. Okay, so these are all the kind of, let's call them even powers, right? Plus, and I can factor out x, and then I have all the coefficients for the odd powers. So I have 12, and I don't have to write x because the x is already outside the parentheses, plus 13x squared, plus 7x to the 4th. And I'm going to call this one to be a sub e of x squared, and this is going to be a sub o for odd of x squared. And why do I say of x squared? Because you will see that these are polynomials in the variable x squared. Okay, only powers of x squared appear, so I might as well express them in the x squared variable. Okay, so intuitively, to compute a on S, because of this decomposition, it suffices to compute AE and AO on S squared, right? Because if I want A at every value of S, here I only have to worry about values of S squared. And by the way, what is S squared? Just maybe in case it's not clear, it is defined to be all the inputs, so all the elements U squared for U in S, okay? So these are the squares of all the elements in S. Okay, and then I could recurse. Now, I do want to make progress, so I'm going to have to pick a set S such that when I consider the squares of all the elements in S, the size of S squared is smaller than S, ideally by a constant factor. Okay, for example, which size would be nice to shoot for? That S squared is what size relative to S? Yeah, for example, S over 2. So let's choose S so that S squared has a size of S over 2. Now, we don't know yet how to do that. We'll see some examples first, okay? But intuitively, if through this decomposition, I only have to worry about things on S squared, why not set things up such that when I considered all the squares of my set, they're actually kind of many collisions, okay? Many things kind of have the same square and have fewer elements to worry about, so that now I have a simpler problem than the one I started with, okay? But there is a question in the chat about, what happens if the polynomial would have higher powers? We would still have only two polynomials. There would not be a of x cubed, okay? It's always x squared, right? Because when I consider all the even powers, I can always write them as a polynomial in x squared. And all the odd powers, once I factor out x, I can always write it as a polynomial in x squared. So let's see an example here. Let's say that I'm starting with a very small set, -1 and 1. And I want to evaluate a at 1 and a at -1. That's what I want to do. Now, through this expression, I know that if I want a of 1, all I really need to do is to worry about what is ae of 1 plus 1 times ao of 1. And if I need to worry about what is a minus 1, then all I really need is ae of 1 minus 1 times ao of 1. But notice that across these two things, I only need a even and a odd on what set? Just one, right? So I have this, I only need it to be the set S squared, which is now 1. The -1 went away, okay? Because -1 and 1 have the same square. Okay, so it's interesting, right? So if I want to evaluate a on the 2 points 1 minus 1, all I really need to worry about is evaluating the two polynomials of half the degree on the single point 1. All right, but this is like a bit of a degenerate example. Let's try to look at a slightly more complex one. And it's more complex because we start using complex numbers, okay? Let's start throwing in I, which is the square root of -1, and minus I, which is minus square root of -1. Let's say that that's my next set, and I want to evaluate A on the 4 points, 1, -1, I, and minus I. If I use again this expression, because 1 and -1 have the same square, 1 and 1, I basically have the same situation as before. And the square of I is -1, and the square of minus I is also -1. So I have some other expression like this. So this time, to evaluate A on the set of points 1, -1, I, and minus I will need to evaluate A even and A odd on which set? S squared equals to what? -1 and 1. So here we start seeing a pattern, okay? If I want instead to construct a set of size 8, I'm going to consider the square roots of all these guys, because here I started here and I took the square roots of all these guys and I went here. Now if I want to double my set size, I'm going to keep taking square roots. And so here I need to take a short interlude on reminding you what are roots of unity, so that we can actually construct the sets that we want. But basically we want to set up a set such that when you keep squaring, it halves the size. And we've just seen, two examples of how that happens for things that should be reasonably familiar to you. Okay. All right, but this is like a very special property of the set S, okay? That we're going to pick the set S so that when you square it, it halves the size, because there will always be two things that square to the same element. Okay. All right, so now we're going to take a short detour on roots of unity. So the definition of the nth roots of unity are all solutions to the equation x to the n equals 1. Okay, that's the definition. there's a question. Wait, there was a wrong notation somewhere. Maybe I should pick it. Oh, there's a bunch of E's everywhere. Sorry, this should be O. Was that the problem? All right, sorry about that. So this should be odd. Oh, yeah. Okay, well, somebody caught it, so it means that something made sense. Sorry about that. But it's a good question I want to answer right away. Why do we care about imaginary numbers if -1 and 1 are good enough to halve? Well, I'm going to have to consider sets S that are arbitrarily large. What other elements am I going to put here? More -1s and 1s, that doesn't work, right? So I have to be able to put in here other things that will let me sort of have this property that when I keep squaring, it becomes smaller and smaller. So you can try to think about whether you're able to put in more elements here with that property. Like what if you want to write a set of size 4, such that when you square it, it becomes 2, and you square it again, it becomes 1. Okay. So, so because of that, we have to talk about roots of unity of higher powers. So what are the roots of unity? What are all the solutions of x to the n equals 1? Well, certainly one solution is 1, because 1 to the n equals 1. And then there's a particular way we write these things, right? They're just a formal way to talk about it. In the complex numbers, which are so-called algebraically closed, so it has all the roots are there. We just give them names. Okay, the principal root is e to the pi I over n, which in polar coordinates you can represent like this. There's a unit circle in the complex plane. There's the real line. There's the complex line, and you just basically take 2 to the pi over n radians up. And here you find e to the pi I over n. And what are all the others? Where they're just further multiple of this one, e to the 2 times 2 to the pi I over n, e to the 3 times 2 to the pi I over n, all the way up to n minus 1 times 2 to the pi I over n. Okay? And not n, because then you kind of go full circle again. So they're basically taking, you're moving by a slice of 2 pi over n radians each time. So kind of you have the roots of unity are kind of spaced out exactly so that, okay, they're not very exact here in my picture, but sort of they're spaced out exactly. So you divide the circle into n slices. Should recall that e to the pi I is -1, so that e to the 2 pi I is 1. And so, for example, you have a bunch of situations where you have the same square. So, for example, who are these 2 points, this one and this one? What are they called? One minus 1, right? So here we have 1, we have -1. Great. How about these 2 points? They also have the same square. Who are they? I and minus I, correct, right? So we have I on the imaginary line and minus I reflected on the other side. Okay. So how about this one over here? Well, this is like the entire circle is 2, right? Half a circle is 1. Half a circle here is a half, right? And half a circle of that is a quarter, okay? So this one, it's e to the pi I, 2 pi I. It's really like it's the full circle is 2 pi, so this is 1/8 of that, right? Or you can think about it as pi over 4, okay? 2 pi over 8 or pi over 4. It's 1/8 of the full circle. And so he's paired up with another root of unity that squares to the same element. Who is it? So I have to add 1 half circle. So I'm adding pi, right? right? If I'm adding pi, it's like adding, you know, let me write it first, then we can see it. It's 5 times 2 pi I over 8, right? Because I'm adding 4/4. Okay, so I had 1/4. I'm adding 4/4, and I get the 5 there. Okay. All right. So these are pairs. Okay, and and we can create roots of unity to create a set such that we can start of size n. Then we square it. We go to n over 2, n over 4, n over 8. Okay. So now we want n to be a power of 2 so that we can keep halving. Otherwise, it's not going to make sense to keep halving. Okay. And our definition of the set S is going to be, for n being a power of 2, let S be the nth roots of unity. So that n squared is the n over 2 roots of unity, and n to the 4th is n to the over 4 roots of unity. So you have this kind of tree where children of the same parent are the ones that share a square, right? Because 1 minus 1 have square 1. And that's true, you know, everywhere here. But then you have I and minus I, they have a square minus I, right? And what's the square root of I? Well, it's this thing over here, e to the 2 pi I over 8. And the other root is this one over here. So we have it there. These two are the other ones. Maybe I'll draw them in green over here. So they are these ones over here. Okay, so those are the 8th root of unity. And so you start out with your original S, and every time you square, you move up a layer in this tree of squares. Okay, so this behavior, roots of unity, especially when n is a power of 2, it lets you set things up so that when you square, you have always two wise collisions, and you have half the elements, and again half the elements, and half the elements. All right. All right. Now, what are we going to set n to be? Where we're going to set n to be 2d plus 1, right? So we're going to need this one to be a power of 2. Okay? And it's okay. Let's just set it to be a power of 2. Let's not worry about now, you know, when it's not a power of 2. Let's assume it is a power of 2. Okay. I presume, you know, sort of complex numbers should be a review. You probably have seen them somewhere else. This is just to kind of remind you that, you know, we're going to be using roots of unity. Okay. And the only reason we're using roots of unity is so that we can set up the situation where squaring everything gives you half the elements. That's the only thing we need. Okay. If there was some other funny set, we would have used it. We couldn't have cared less about roots of unity beyond that. Okay. All right. So just pause for a moment. Are there, you know, pile up of questions, or are we traveling smoothly?
No pile up in the chat right now, but if anyone wants to jump in, go ahead.
Yeah, so the basic idea is squaring. By the way, why does squaring show up? Because that's how we split up our polynomial, right? So we like other splits could have caused caring about different operations. We're not going to explore them now, but because we split our polynomial this way, it said that we specifically care about the square of the elements in our domain. Okay, and you know, given that that is the case, we said, okay, fine, let's go on a hunt looking for a set that is well behaved under squaring. Well behaved meaning that it halves in size every time you square everything inside it. Okay. And half the size when we want to make progress. Okay. So now that we have this under our belt, let's write out the algorithm. Okay. So now we're going to write the fast Fourier transform. Okay. So the fast Fourier transform is an algorithm for evaluating the polynomial over roots of unity. So we're given as input the coefficients for the polynomial a of x. Okay. So that is the polynomial a of x that is specified as coefficients. And here, you know, I've switched from d earlier, the letter d, to the letter n, just because I wanted to keep the letter n for the roots of unity. Doesn't matter. So we have, oopsie, we have a polynomial of degree n, okay? And maybe some of these are 0, right? Because we may have had to do some padding, for polynomial multiplication later. It doesn't matter, right? So we have some polynomial here, and we want to evaluate it on all the roots of unity. Now, because it's kind of awkward to keep writing e to the pi I over n, a common notation for the principal root of unity is the letter omega, okay? So we're going to evaluate it on omega to the 0, also known as 1, omega to the 1, also known as omega, or e to the pi I over n, and omega squared, omega cubed, blah, 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 all the way up to omega to the n minus 1. So these are the n roots of unity. Okay, these are all, we're evaluating A on the set S that consists of the nth roots of unity. That is the specification of what the algorithm aspires to do. Now, how does it actually do it? Well, first we're going to do the split of even powers and odd powers. So here we are. We're saying pick A0, A2, A4, up to an minus 2. Why? Because these are the coefficients of all the even powers. Then pick A1, A3, A5, all the way up to an minus 1. Why? Because these are the coefficients of all the odd powers. Okay? And now we want to tell, run yourself, this is a recursive call, on the polynomial specified by coefficients AE and AO on the set S squared. Okay? But the set S squared is specified by omega squared, right? Because if before our set was, let's start, for example, with, let me use a different color, green. Let's say the case when n equals 8. So our set was to start with the 8 roots of unity, okay? When we square, we're going to get just 4 roots of unity. This one, this one, this one, and this one, okay? Now, this was omega, right? This was omega squared. This was omega cubed. This omega to the 4th, omega to the 5th, omega to the 6th, omega to the 7, and this is 1, which is the same thing as omega to the 8, okay? The set S was described by omega. Now the set, so that was S, you can think about it, everything generated by omega. And the set S squared is everything that's generated by omega squared, right? Because that is the step given by omega squared. That you jump by 2 steps each time. Okay? So that is why to represent S squared, we pass the parameter omega squared instead of omega. Okay? Now, when we run these 2 subroutines, we are going to obtain the evaluations of the 2 polynomials on S squared. Okay? So what is that? That is AE of omega squared times 0, because it's to the 0, right? Omega squared times 1 is omega squared to the 1. Omega squared times n minus 1 over 2, right? Because we have half of them, right? And the very same thing for the other recursive call, because both of them are evaluating the polynomials on the set S squared, right? Now we have the evaluations of the 2 polynomials on the set S squared. We have to construct the evaluations of A on S. But remember our expression, let me write it in a different color yet, in red. Our expression said A at some value x equals AE x squared plus x AO of x squared, right? So let's say I'm interested of the value of A at omega to the I. Well, I have to use the value of AE at omega to the 2i, right? Plus omega to the I, that's fine. I mean, I can just plug in omega to the I myself, times AO omega to the 2i. Now, where do these things come from? Well, they come straight from here, right? And what happens for the second half? Well, I can reuse things, right? Because when I square this, it has the same square. Let's put it like this. Oopsie. Omega to the I squared is the same thing as omega to the I plus n over 2 squared, right? Because that is, omega to the 2i times omega n, and that's, omega to the I times 1, right? So these two have the same square, which is this one here. This is why we set S up this way. So I am basically figuring out as a pair the value of omega to the I and its friend, omega to the I plus n over 2. Both of them have the same square. And so I can reuse the same values. Obviously, there's a slightly different expression in the second one, but it doesn't matter. I'm reusing the same values to construct this entire thing, okay? And then I will output the values of A at omega to the 0, omega to the 1, all the way up to omega to the n minus 1, okay? Which is what I wanted to achieve. All right, so before maybe we go over it again, let's at least talk first about the running time of this algorithm. There is a recurrence relation I can write. Can anybody tell me the recurrence relation? How many recursive calls are there? Right, so there are 2 recursive calls. Where are they? Well, number 1 here and number 2 here. So that's the 2 recursive calls. T of, well, how big is the input? Well, right here, we halved the input size, right? Because half the coefficients go here, the other half go here. So we have 2 recursive calls on inputs half the size, right? And then I have a recombination cost, which is over here, which is a linear number of operations, because I have a loop that goes from, that consists of n over 2 things. And in each time, I'm making a constant number of operations, okay? So it's plus order of n, okay? And this works out to be order of n log n, right? Because this is the balanced case. This is a balanced tree. At every tree, so at every layer of the tree, I'm paying order of n cost, and there are log n layers in the tree. So overall, it's n log n. All right, but there's a, let me just rewrite this ugly exponent here. That should be n minus 1. All right. And we can do this, if you're uncomfortable with these, I mean, hopefully by now you are comfortable with the master theorem, but if you want to see it directly with the master theorem, we have A equals 2, B equals 2, D equals 1. D is not the degree, it's the D of the master theorem. So the magical expression A divided by B to the D, which is 2 divided to the 1, equals 1. So we're in the balanced case, and we know that it is O of n to the 1 times log 2 to the n, right? So just the mechanical way of doing it. All right. Now, before I continue here, let me just pause for a moment. We have just seen the fast Fourier transform, okay? It is an algorithm for evaluating the polynomial that was given to us over the roots of unity, okay? Chosen to be, a number that is a power of 2. And how does it work? We split the polynomial in even and odd, so that we only have to care about the squares. Because we've chosen roots of unity this way, the squares halve in size, like going from green to blue. We do 2 subroutine calls to solve the problem to evaluate the even powers on the squares and the odd powers on the squares. And we recombine, using, for each of the 2 pairs of elements that square to the same object, we have the expression given by this one. We reconstruct all of these and then we output them, okay? Okay, so let me pause here for questions on this algorithm specifically. Okay, there's a question to explain the recombination step. So it really is, let me just move it somewhere here. So we agree on this formula here, right? That this is how we split our problem. Let's say that I want to evaluate A at omega to the I. Well, what do I need? It's AE omega to the I squared plus omega to the I times AO omega to the I everything squared. And this thing right here is exactly this expression over here, right? Now, why do I have a second expression here? Let's call it triangle, because I want to consider together two pairs of elements in S that square to the same thing, right? A to the I plus n over 2, which is the diametrically opposite one to omega, right? Remember that before here, there was a reason why we're looking at these pairs, right? So these two square to the same thing, these two square to the same thing, these two square to the same thing, these two square to the same thing. They are like, you know, like a half a circle away, okay? So this plus n over 2, which is kind of what I also computed over here, why is there a minus there? Okay, right, yeah, because it squares to the same thing. This one squares also to that thing over here, right? Because we just tried it here, right? If you omega to the I plus n over 2 is omega to the I, which is times to omega to the n over 2, which is omega to the I times e to the pi I, which is minus omega to the I. So when you square it, you get omega to the 2i, all right? So here, we're going to get AE, the square, well, that we already checked, that's omega to the 2i, plus omega to the I plus n over 2 times A0, the square, which is omega to the 2i. And that's the triangle expression. So I am basically I'm computing the n outputs in n over 2 pairs. Okay, so hopefully that kind of clarifies the recombination step. Let's see, are there other piled up questions or?
There were some questions about steps 2 and 3. Would the n minus 1 over 2 in parentheses be n over 2 minus 1?
So this part over here?
Yeah.
Well, we should ask if S is 1 omega squared up to omega n minus 1, then what is S squared? Well, it is going to be 1 omega squared, omega to the 4th, all the way up to omega to the n minus 1, right? Which is also known as, I can rewrite it differently, omega squared times n minus 1 over 2, right? Because there are pairs of elements that collided into the same square. So I have half of them. That's why we set up this S squared to have half the size. And so we're just writing here all the powers of omega squared as far as there are, right? You know, there's no more powers beyond n minus 1 over 2. Okay, so this is the blue things here are just S squared.
Thanks.
So, Professor, the bases in the fast Fourier transform are just the unity, like roots of unity?
So I'm not sure if I would call them bases, just the set S that we're using are the roots of unity. Indeed, here, the set S that over which we're evaluating are all the possible roots of unity, right? Omega to the 0, omega to the 1, I mean, the nth roots of unity, right? So you see this set here is exactly the inputs to A here. All right, more questions. Why do we get order of n for the recombination cost? Because we have n over 2 iterations And in each iteration, we do a constant number of operations. Why? Because we have already computed all these things, and we are just recombining. We're doing this plus this times that is this one. And then this plus this times that is that one. So that's a constant number of operations for n over 2 loops. So that's like overall order of n. There's a question about, isn't this one an odd exponent? Remember that n is a power of 2, but we are 0 indexed. So the last one is always odd, okay? So also here, n minus 1 is odd. You can also see it here. That it corresponds to an odd power. Okay, explain the gray equation on the right. So this equation here, we are establishing that the expression for the other, so we're basically looking at, establishing that this one and this one have the same square. Okay, so let's do it. Omega to the I plus n over 2, I just split it into two parts. Omega to the I times omega to the n over 2. Now, omega is e to the 2 pi I over n. So if I multiply by n over 2, I'm left by e to the pi I. E to the pi I is minus 1, so I have minus omega to the I. And when I square it, I get omega to the 2i, just like what I would have gotten if I would have squared omega to the I. So these two have the same square, which is omega to the 2i. And again, these pairs are tied together like these two, these two, these two, these two. So they're like, across, they are like on at the two ends of a diameter of the circle. Okay, they square to the same thing. All right, more questions. Okay, that's as much as I wanted to say for today. I will have in the posted slides also one additional slide on interpolation, but I don't want to talk about it right now. I think it's better to first absorb the evaluation part. Kind of popping back up, what we did was just basically show that with a suitable choice of S, we can do evaluation in D log D, okay? So that we can do this part in S log D, in D log D, and then we'll see in discussion how to do interpolation. It's just basically like a symmetric operation, so you can use the same FFT algorithm just with slightly different inputs. Okay, so with that, I think I'm going to stop the recording and stick around for questions.